This is lesson 80, VHDL example 52. And in this example we're going to write a VHDL program for a clock divider. We'll illustrate the use of this clock divider by designing a modulo 10k counter that's going to count on the 7-segment displays from 0000 to 9999 and then wrap around. Okay, this table shows the clock divide frequency starting at 50 megahertz. Remember, we have a 50 megahertz clock coming into the FPGA, and we're going to make a 24-bit counter. And this table shows Q0 to Q23 starting at Q0, which, as you remember, is half the frequency of the 50 megahertz. So this will be 25 megahertz. This will be 40 nanoseconds. We show the period in milliseconds here, and we'll show the frequency in hertz. Q1 will be half of this frequency, so Q1 will have a frequency of 12.5 megahertz. And it keeps going down for every Q, and if you finally get down here to Q17, for example, we'll be all the way down to 190 hertz. We're going to use this one to drive our 7-segment displays. That is, we'll multiplex it at a 190 hertz rate. If you get down here to Q19, that's about a 48 hertz one. We'll use this for our modulo 10k counter, so we're going to count 48 times a second. So we'll go fast enough so we can get through 9,999 in a quick time. And all the way down to Q23, it's about 3 hertz. So for a 24-bit counter, the last Q, Q23, will actually count once every third of a second, roughly. Okay, we're going to illustrate this by designing this top-level design. This is going to be our clock div. We have clear coming in, and M clock is our 50 megahertz clock on the FPGA board. And we're going to tap off 2 of the Qs. Q17, you remember, is going to be a clock 190, we'll call it. This is our 190 hertz. We'll make a modified version of our X7 seg B. I'm going to call it X7 seg BC, indicating it's a low frequency clock coming in. Remember, the X7 seg B we've used before just has M clock coming in, and we essentially built a 24-bit counter inside here. Well, now, since we have a 24-bit counter here, we'll just tap off the Q190, and now we only need a 2-bit counter in here. We'll also tap off clock 48, our 48 hertz one, and that will drive our Mod10k counter, which will be a modification of our modulo 5 counter that we did. We'll just make it a modulo 9999 counter. And then we'll modify the binary to BCD converter that we did back in lesson 34 and make it a 14-bit counter, since we have 14 bits coming out here for our 9999. So let's look at clock div first. M clock and clear come in, and clock 190 and clock 48 come out. So we make Q a signal, 24 bits, 23 down to 0, and then it's our usual counter. Now it's M clock and clear coming in. If clear is 1, we'll set Q to all zeros. Here I've indicated, since it's a hex number, since I'm going to have 6 hex digits in 24 bits, I can write it X and double quote 000000. I could have put the others go to 0 here as well. And then else if M clock tick event and M clock equals 1, M clock's the input here, then Q just gets Q plus 1. So this is our counter. And then our outputs, will tap off 2 of them. Clock 48 is Q sub 19. Clock 190 is Q sub 17. So when you use clock div, you can tap off however many you need. Sometimes you'll need only 1, maybe clock 190. Many of our programs later on will use 25 megahertz clocks, in which case we'll use a clock 0. That gives us a 25 megahertz clock. And you can use whichever ones you need here. Okay, here's the modification of our modulo 5 counter. We'll make it a modulo 10,000 counter. Clock clear in Q is now 13 down to 0, since we need a 14-bit output to count to 10,000. Make a signal count, 13 down to 0. And then in the process, here's our asynchronous clear again for the count. Else on the rising edge of the clock, if, now count, remember standard logic vector, so I want to compare it to 9999. So for convenience, I'll just convert integer count. So if convert integer count, that is if the standard logic vector count is equal to 999 decimal, then I want to reset count to 0. Here I use the others. Else, we just increment the count. So this is going to be a modulo 999 counter that when it gets to 9999, it will go back to 0. Let me just set Q to count. Okay, well now we need a 14-bit binary to BCD because we want to display this on the 7-segment display in decimal. Well, you remember back in lesson 34, we did an 8-bit binary to BCD converter. We also did a 6-bit, maybe a 16-bit. So here we'll modify it to be a 14-bit. B now has to be 14 bits. P is going to be, it's going to contain the BCD numbers, will be 17 bits. And remember, we initialized the Z to 0. Z has to be 32 down to 0 now. And then remember, we shifted B 3 bits to the left. And then now we have to go through 11 more times to get to 14. And then we check the units, the tens, the hundreds, and the decimals, each time seeing if the units is greater than 4, we add 3. Remember the algorithm. We shift Z 1 bit to the left. And when you get done, P is going to be 30 down to 14. So that's going to be a binary to BCD 14. And now we're going to modify our X7 seg B. We're going to call it X7 seg BC, in which the input, instead of being our 50 megahertz M clock, is now, I call it C clock, which is going to be our 190 hertz clock that we get from our clock div. Other than that, it's the same as we had before, except now our S signal to our 4-bit multiplexer is going to multiplex the 4 digits on the 7-segment display. We only need to be 2 bits, so it's going to be 1 down to 0. Other than this, we will set our A enable just like we did before. You can go back to lesson 28 where we did the X7 seg B to see how this works. This is going to give our leading blanks. Here's our quad 4-to-1 multiplexer. Here's our 7-segment decoder. This is all the same as we had before. Here is the AN code, the same as we had before. And now we just modify this to be a 2-bit counter. So this is C clock clear. If clear is 1, S just gets 0, 0. Else on the rising edge of the clock, S is S plus 1. So we'll just build in a little 2-bit counter here to multiplex the 4 digits on the 7-segment display. So let's make a top-level design. Here's the top-level design. M clock's coming in. Here are the button. We'll just have button 3 down to 3. This is just for our clear. And then the output of the 7-segment display, we need A to G, AN, and our decimal point. Then we'll list our components. Here's the component for clock div. Here's the component for Mod10k count. Here's the component for our binary to BCD 14. And here's the component for our X7 seg BC. And then we just have to port map them up. We'll need a signal B, 14 bits. We'll need a signal P, 17 bits. We'll need signals clear, clock 48, clock 190. Clear is just going to be button 3. We'll just wire up the clock div, setting clock 190 and clock 48 to the signals here. M clock is the input. We'll port map our Mod10k. Q goes to the signal B. And then we'll binary to BCD14. B is the input, P is the output. And then our X7 seg BC, X is going to P15 down to 0. That's the 16 bits, which is going to display the 9999. And C clock is our low clock 190. So that's our 190 hertz clock. So this is the top level design. This would be a good one for you to compile and implement and download to your FPGA board. And when you run it, the 7 segments display should count fairly rapidly from 0000 to 9999 and then wrap around.